Bismillahirrahmanirrahim. In this, we are going to discuss some solved examples related to the DC motors. The first example is related to the DC shunt motor. It is operating at 110 volt and it is drawing 2 ampere at no load state. Armature resistance is 0.2 ohm, field resistance is 110 ohm. We are supposed to determine the efficiency and the speed regulation when the load is changed to 10 ampere by applying a certain load. So for the efficiency calculation, we will have to calculate the losses in the machine. So as we discussed in our previous tutorials, first step is to draw the equivalent circuit diagram. So as it is a shunt motor, so your field winding and the armature winding, they will be in parallel. So field winding F1 and F2 and the armature winding A1 and A2 that you can see over here are connected in parallel. Armature resistance is 0.2 ohm, field resistance is 110 ohm, and the supply that is connected is of 110 volt, and at no load machine is going to take 2 ampere, so that is mentioned over here, no load current of your machine. Okay, so as your machine is connected in the shunt configuration, so the voltage across this field will be equal to your terminal voltage. So current in this can be determined that IF will be equal to V over RF. We will not consider this inductance because this will be short circuit in the DC, and we are assuming that the machine is operating at the constant current, so no role of this inductance. So the total resistance of this branch will be 110 ohm. So using that we can determine the field current, and that you can see is calculated in this first step, that is Vt by Rf, that is 110, that's the volt we are going to apply, and this is the resistance of the field winding. So 1 ampere is the current in the field winding. So this current is 1 ampere. Okay. Now what will be the copper loss because of the flow of the current in this winding? So that will be determined as IF square into RF, right? So that is calculated in this step 3, that IF square into RF, 1 ampere is the current into 110 ohm is the resistance. So 110 watt will be the power loss in the field winding, and that will remain constant if our voltage is constant, because if the voltage is going to change, then the current over here will change, and then this current will change. So in the shunt configuration, usually the field copper loss remains same, so it will be a sort of constant loss that is taking place in your machine. Okay, now let's determine the armature current, because we know about the total current from the source, that is 2 ampere, and we have calculated the current in the field winding is 1 ampere, so the difference is going to flow in the armature, right? So that can be calculated with the help of this equation, no load, so source current minus the field current, so 2 ampere minus 1, so 1 ampere is the current that is going to flow in the armature at the no load state. And what will be the copper loss when this current is going to flow in this winding? There is the resistance, so Ia square into Ra will be the power that is dissipated in the form of heat in the armature, and of course it depends upon the armature current, and it is going to take place in the copper winding, so we call it the armature copper loss, and that can be calculated over here, Ia square into Ra, so 1 into 0.2. So 0.2 watt is the copper loss, very small current in the armature, and the resistance is small, so very small power loss at the no load state, only 0.2 watt. Okay, now what will be the back EMF over here? That you can work out by writing the voltage equation. So the voltage that you are going to apply over here is Vt, right? So out of that, one voltage drop will be there across this resistance, and that will be Ia into Ra. So if you subtract this one from this terminal voltage, the remaining voltage will be over here as a back EMF. So back EMF will be equal to Vt minus IaRa, 110 volts you have applied, armature current 1 ampere, and the resistance is 0.2, so 109.8 volt. So the back EMF over here is 109.8 volt at the no load state, right? And because of this difference, 110 volt over here and 109.8 volt over here, the current is going to flow, and that is going to be the 1 ampere in this particular state when the total current from here is 2 ampere. 1 ampere is going towards your field, and the rest of the 1 ampere, because of this potential difference that is between back EMF and the terminal voltage, the current is there in the armature. So we have calculated all the things at the no load state when there is no mechanical load connected with your machine. So your machine is rotating, it is drawing certain power to run itself. So let's suppose it is rotating in this direction, and the induced torque is of course in the direction of speed, and the load torque will be in the opposite direction when applied. At the moment it's a no load state. Okay, so there are certain other losses which are going to take place in your machine as well. Those are the frictional losses when your machine is rotating. So frictional loss and the windage loss over here because of the air friction. So usually those are considered as fixed for a particular machine, right? So those are the mechanical losses, and the other losses which are going to take place in the machine are the core losses or the iron losses, which are basically representing the hysteresis loss or the eddy current loss in the core. And as there is no change in the frequency over here, so those are going to remain constant. So iron losses will be constant, and the mechanical losses will be constant. So iron and the frictional and the windage losses together can be assumed to remain constant between no load and the full load, because when the current is going, when the load is going to change, armature current is going to change, and all the other parameters are going to remain constant over here. So those will be considered constant. So how to determine those ones? You know what you are injecting in your machine, that's the total input power, and from that if you subtract the losses in the field winding, and then you subtract the losses in the armature winding at the no load, remaining power is basically the loss which is going to take place in the core, or those may be considered as iron losses, and is being lost in the friction and the windage of your machine, windage loss in your machine, because you have not applied any load, your load torque is 0. So that's why the whole of the rest of the power will be considered as the constant loss. So that can be determined. So your input power, that is 110 volt multiplied by 2 amperes, so that is the input power. Then 110 watt is the loss in the field circuit, and zero 0.2 watt is the loss in the armature. So 109.8 watt is that power which is being lost because you are not connecting any load at the moment with that one. So that is the power that is lost in the core and as a friction or in the windage. So that will remain constant, either it's a no load or the full load state. When you will apply the load, more current will be drawn from your armature to provide power to the load, and that will be drawn to overcome the frictional losses, windage losses, and the iron losses in your machine. Okay, now let's take the second part over here. If you look at the statement, now the load is increased and the armature current is going to supply current is going to become 10 ampere at a certain load. So we need to look at that what will be the new set of losses at this operating condition. Okay, so now the equivalent circuit that is done over here, that is going to remain same. So now we are going to recalculate this some of the things. For example, the armature current in the loaded state that you can observe over here, that will be the supply current in the loaded state, that is given to us 10 ampere. Field current will remain same because no change in this. In order to change the field current, you will have to connect a variable resistance over here, but in this particular example no change in the field current because no variable resistance is there, and the field resistance is 110 ohm. So terminal voltage is not changed, so field current will remain same, that is 1 ampere. So now armature current is changed to 9 ampere because our supply current is changed to 10 ampere. 10 ampere minus 1 ampere, the rest of the current, that is 9 ampere, is going to flow in your armature. Okay, so armature copper loss is going to change. No change in the field copper loss because IF square RF, that is going to remain same. But the armature current has changed, so armature copper loss is going to change. So we need to recalculate it, and that is equal to this one, IA square into RA. So the 9 square into 0.2, so 16.2 watt is the power that is now being lost in the form of heat across the armature. Okay, now the current over here in the armature has changed, and for that this EB must be reduced. That has reduced. So how to calculate the new EB? So that is equal to the back EMF in the loaded state, that is equal to VB minus new armature current into armature resistance. So 110 volt minus 9 into 0.2. 0.2 is the armature resistance, new current is 9 ampere. So 108.2 volt. So the new back EMF, this one is 108.2 volts, so that you can compare it with the previous one. Over there it was 109.8 volt, or over here it is 10.8 108.2 volt. A small change in back EMF has brought a large change in the armature current, that is from 1 to 9 ampere. Okay, now let's calculate the total losses which are going to take place. One is the armature copper loss, the other one is the field copper loss, and the constant losses which are going to take place. Those are basically the core losses, and the frictional and windage losses, they remain constant, they are not going to change with the load. So the total loss is now 16.2, 110, 109.8, so 236 watt is the loss in the machine. Okay, so now to find out the input power, the efficiency is the output power of over the input power. So for that, the output power, we can write it like that: input power minus losses. So if you subtract losses from the input, the rest is the output power, so it can be written like that. And similarly the spin, and the spin is terminal voltage into supply current, right? That's the input power over here. Terminal voltage is 110 volt multiplied with supply current, that is 10 ampere. So that will be the total input power, and the losses that you have calculated over here. So over here 110 volt is the voltage, and this is the current, supply current. This is the input power minus 236 watt loss that we have calculated over here, over the input power, that is 110 into 10. So that is 0.784. So 78.4% efficiency of your machine. It means whatsoever you are going to apply as an input to the motor, it is going to convert it into the mechanical form, but there are certain losses which are going to take place in your machine, and only power that you are going to get at the output is 78.4% in this particular case, based upon armature resistance, field resistance, and other constant losses which are going to take place in the machine. Okay, now how you define the speed regulation, because we need to calculate the speed regulation over here, that you can see. So speed regulation is basically the variation in the speed from loaded state to the no load state. So no load speed full load speed to the full load speed minus the no load speed compared with the no load speed. So what was the speed at the full load state minus the speed at the no load, comparing it with the no load, is going to give you the speed regulation, percentage change in the speed. Of course, speed information is required for that one, but that is not given to us in this example, that what is the speed. So we will be taking another way to compare, to find out this speed regulation. And what is that? We know that the back EMF is proportional to k phi into omega, right? So if we consider the no load state, we can write it like that: k1 phi 1 omega 1, and for the full load or the loaded state back EMF2, that will be equal to k2 phi 2 into omega 2. And you can also express this one in terms of RPM, some k1 prime, let's suppose phi 1 into n speed in RPM, and k2 prime phi 2 into n2 the speed in RPM. So now the speed, as our flux is constant, as we have the shunt machine, the flux is not going to change. The flux over here, you can see the field current was 1 ampere over here in this case, and over here it is also 1 ampere. Speed, the flux has not changed. So we can say that this is equal to some constant k into n1, and this is some constant k into n2, because flux is not changing. So our speed is proportional to EB1. So N1 is proportional to EB1, and N2 is proportional to EB2. So instead of using the speed, we are going to relate it with the back EMF. So loaded back EMF, when the current, supply current has changed to 10 ampere, and then this no load back EMF when the supply current was 2 ampere, right? So we will be using the back EMFs over here. So if you plug in the values of the back EMF in the loaded state is 108.2 volt, and the back EMF at the no load is 109.8. So taking the values, so your speed regulation is minus 1.4%. So what that means, that the change in the speed, if you just consider the absolute value over here 1.4%, so when you are going to change the load over the machine, so change in speed will be 1.4%. 4-5% from the case when the input current was 2 ampere and when the input current is 10 ampere. If the current is increased, load is increased, so the change in the speed. So this is giving you information at how much speed is going to change in your machine. Okay, so if I summarize this example, we have considered the losses in the machine. We have seen how to calculate the losses in the machine, how to calculate the constant losses, and how to calculate the back EMF in the loaded state, and then the variation in the speed. Okay, so our next example is related to the DC shunt motor that is running at 1000 RPM and drawing a current of 12.5 ampere from 110 volt DC source. Armature resistance and field resistances are given. Speed of the motor when it draws the current of 2500 ampere and 110 volt supply is to be determined, and because of the change of the load, the flux has changed, and that is to be considered 3% due to the armature action. Armature action is going to take place when you are going to change the load, that is going to change, and we have discussed the armature action in detail in the theory class. Okay, so now first of all, let's draw the equivalent circuit for this one. So the equivalent circuit, as it is a shunt motor, again you can see the field winding F1 and F2 that is in parallel to the armature A1 and A2, and 110 ohm resistance of the field and the armature resistance is 0.1 ohm. Supply current is 12.5 ampere right at the starting condition with the applied voltage of 110 volt, and machine is running at the speed of 1000 RPM and at this particular state. Okay, so that is given to us, that is 1000 RPM. So as a first step, we have drawn the equivalent circuit. Now we are going to find out the field current as we did in the last example. So IF is equal to VT by RF. So 1 ampere is the current that is going to flow in the field winding, right, and that is simply determined by dividing the voltage with the resistance, right. So that is 1 ampere, that is the field current IF. Okay, now the total current that is known to us from this supply is 12.5 amperes. So our armature current will be simply the difference of the supply current and the field current, and that is 11.5 ampere. And then you can work out the back EMF as we did in the last example. So using the motor voltage equation, so VT minus IA1RA, so that is 108.85 volts. So the back EMF in this case is 108.85 volt. Okay. Okay, now when the load on the machine is going to change, so its supply current is going to change, and the load is basically what we have connected with the shaft. It was rotating with a certain speed, it was giving you the induced torque, right, and the load torque was acting in the opposite direction. So at a one particular load it is drawing 12.5 ampere. Now if we are going to change the load on the machine, of course its speed is going to change, and its induced torque is going to change such that the load torque is fulfilled, load torque is available. So what is the change in the armature current if the supply current goes to 12.5 ampere? So we know that the current in this branch is 1 ampere. It is not going to change because the voltage is going to remain constant, 110 volt. So the current in this branch is fixed, that is 1 ampere. So we can work out armature current, that will be the difference of this current and this current, right. So armature current IS minus IF 25 minus 1, so that is going to be 24 ampere. Now we are going to work out the new back EMF because of the increase of the load. So that is VT minus IA2 into RA, so that is 107.6 volt. So this back EMF is now 107.6 volt, and that you can see has decreased, and because of decrease in this back EMF compared to that one, the current over here is significantly increased from 11.5 ampere to 25 ampere because of the increase of the load over here. More load torque, more induced torque is required, more current is required over here, and for that this back EMF will have to go down, right. Okay, now comparing the two states, as we have discussed in the previous tutorials as well, how to work out the new speed. So first back EMF, that is equal to K phi 1 N1, that is at one particular state, that was when the current was 12.5 ampere, and the second back EMF equation, that is K phi 2 N2, when you have the new load of 25 ampere and new flux as well. Okay, the flux is going to field current flux is going to remain constant, that is because it is going to give you fixed 1 ampere current, but armature reaction, because of armature reaction the magnetic neutral axis is going to shift, and because of that the net reduction in the field current, so because sorry, net reduction in the flux that is available at the poles, so that is reduced by 3%. Okay, so what was the initial flux? Let's suppose that is equal to 1, and what is the second flux, the new flux? It is 0.97%, 0.97 times of phi 1, because there is the reduction in the flux by 3%, that is given to us because of the armature reaction. The net flux weakening is there, and because of that 3% reduction in the flux, so the new flux will be 0.97 times phi 1. So just using this equation, rearranging it for N2, because we have taken the ratio of these two as we have considered in the previous tutorial as well. Please go through those tutorials for the details. So N2 will be equal to this one, EB2 into phi 1 into N1 divided by EB1 into phi 2, and phi 2 is 0.97 times phi 1. So this phi 1 and phi 1 will be cancelled out, so you are left with EB2 N1 divided by 0.97 into EB1 to get new speed, and if you plug in the values, that is 1019.08. so the new speed is 1019.08 rpm, and the previous speed was this one, 1000 rpm. Although you have increased the load, so for that the speed should decrease. Yes, the speed will decrease if you do not consider this change in the flux, because it is reduced by 3%, right? So if you neglect that change in the flux, if you consider that one constant, okay, there is not or you will observe that the new speed is lesser than the previous speed when you are going to increase the load. But now we are considering the armature reaction. Armature reaction is going to reduce the flux that is available at the pole by 3%, and you know that the speed of the machine is inversely proportional to the flux, right? So if the flux is going to reduce, the speed is going to increase, and that's why you are going to observe the increase in the speed over here. So armature reaction in the DC motors particularly will increase the speed. In the case of generator, it will reduce the induced EMF, but in the case of motor, it reduces the flux. Net flux is weak at the poles, and because of that the speed is going to increase. So because of armature reaction, you are going to observe the higher speed. Even though our load has increased, the armature current has increased from 11.5 ampere to 24 ampere, but the armature reaction is to be considered, right? So in the previous examples, in the previous tutorials, we have not considered the armature reaction. That's why the speed was always decreasing with the increase of the load. But here it's an interesting example. Here you can see that if you consider the armature reaction, and of course at the moment we have just considered 3% reduction in the flux, it may be the lesser, it may be the more, that will be evaluated in the upcoming tutorials related to the DC motors. So in this particular example, I have considered 3% reduction in the flux. So if that is the case, so you can observe your speed is going to increase with the increase of the load, because increase of the load, that is basically the increase of the armature reaction, and because of armature that is the increase in the armature current, and because of the armature current, the armature reaction is going to increase, and because of that there is the flux weakening. So we have discussed its effects in the theory class, that because of the armature reaction there is a shift in the magnetic neutral axis, there is the decrease in the net flux of the machine, and what are the possible remedies for that one? Change the position of the carbon brushes, or change the introduce the interpoles, or use the compensating winding to compensate that change in the flux that is being brought by the increase of the armature current. Okay, so that's all from this video. Thank you very much. See you in the next tutorial.